I have posted the YouTube live streaming link on the chat box also. If the participants joining this event is more than 500, then you can share this YouTube live link with your other colleagues so that they can enjoy this stage show on YouTube channel also.
Hello.
Parvesh sir, am I audible? Parvesh sir, am I audible?
सर सामंता सर भी आ गए हैं, उनका माइक का भी म्यूट है।
हेलो, ओ अच्छा, नो
हाँ उत्तम सर बोलिए सर।
हाँ, आवाज क्लियर सर? आपको आवाज आ रही है? दुबे सर मेरी आवाज आ रही है आपको?
हाँ
क्लियर आवाज। हेलो।
अभी एक मिनट आते हैं। আমারটা কোনটা রে? এটা তো উত্তম শর্মা লিখছে নাকি? এটা আমারই কি? डॉक्टर दुबे,
यस सर।
डू यू हियर मी नाउ?
यस सर, आपकी आवाज आ रही है।
अच्छा ठीक है।
इजीली ऑडिएबल।
गुड मॉर्निंग।
गुड मॉर्निंग टू ऑल। गुड मॉर्निंग सर। हीरा बल्लभ, नमस्कार।
कैसे हैं?
बढ़िया है सर।
गुड मॉर्निंग प्रोफेसर विजय।
गुड मॉर्निंग सामंता जी। उनके गुड मॉर्निंग कर लें, फिर माइक्रोफोन म्यूट कर देंगे।
यस सर।
विजय सर गुड मॉर्निंग।
गुड मॉर्निंग।
सामंत जी आपका वीडियो ऑफ है।
हाँ वीडियो ऑफ है। लेट मी ओके ना?
यस सर, इट्स ऑल राइट।
It's right. No, actually, make them off.
हेलो, नमस्कार।
नमस्कार प्रोफेसर जोशीपुरा।
Yes,
नमस्कार सर। नमस्कार
विजय सर, Professor Samantha, the leader of the team today, Professor Samantha sir.
नमस्कार। नमस्कार जोशीपुरा सर।
Hello sir. Fine, very nice.
Good morning everyone. Good morning teachers. Namaskar.
सब नमस्कार।
नमस्कार।
गुड मॉर्निंग सर विजय जी।
गुड मॉर्निंग सर संजय सर।
जोशीपुरा जी गुड मॉर्निंग।
नमस्कार।
नमस्कार।
सर गुड मॉर्निंग।
हाँ गुड मॉर्निंग।
हेलो उत्तम शर्मा जी।
सर नमस्कार।
Yes sir, good morning.
नमस्कार।
Yeah.
BN Das sir,
हाँ जी, good morning.
प्रणाम
Good
प्रणाम
morning.
नमस्कार।
Good morning.
Das,
Namaste.
Das sir, good morning.
Very
Good
nice, very
morning.
happy to see you. Very happy.
Good morning, Das sir. Good morning.
वेलनकर सर भी आ गए हैं।
हाँ सर, नमस्कार।
नमस्कार
Good morning. नमस्कार सर।
हाँ, दुविदी, नमस्ते.
So before going to start our this program, we will have a short video of Dr. D.P. Khandelwal sir by Y.K. Vijay sir. We are very soon we are going to play that particular video before starting our event from sharp 10 a.m. So within a 2 minutes we'll start that video.
All the guests, chief guest and others are here.
Yeah, I will talk to chief guest right now, sir. He will join at
And
9:55.
Professor Vijay Singh, President. Our President, Professor Vijay Singh.
He has yet not joined, sir.
If you can call him.
Yeah.
So today in the whole of India, there is National Science Day, National Science Day.
Yes.
Good.
I remember the very first National Science Day was launched 1987-88, and we organized a Gujarat state level quiz competition for students.
Mhm.
All the students came there, and there was a general talk about Raman effect, and it was very nice. Very nice.
Dr.
That was the
Vijay
first event.
joined within 2-3 minutes.
Since then, every year we arrange some program on National Science Day, on or around, depends on the convenience.
So Dr. Vijay Singh and Dr. Upinder Dhar will join shortly within 5 minutes.
Oh yes, very nice. We are on the YouTube channel.
Yes, sir. We are on the YouTube also.
Very nice, very nice. Thank you so much, Uttam Kumar Sharma ji. यहाँ पर 3 शर्मा हैं. There are 3 Sharma Jis. One is our Sanjay Kumar Sharma ji. The other is Dr. Uttam Sharma, and the third one is Om Prakash Sharma. And we are going to meet Om Prakash Sharma tomorrow also.
All the
There will be a Gujarat level program tomorrow.
Sir,
Okay.
what 3 Sharma means SSS.
You are right.
Science stage
Ah.
show.
Science Stage Show, Sharma.
Yeah,
Wow.
sir. And
Great.
means
Lovely.
combination is Satyam Shivam Sundaram.
ठीक है, बहुत 3-dimensional presentation. 3D, very nice. Oh yes.
Dr. Anand Krishna is there, creator of SSS.
Is he there? Anant Krishnan. He's
Dr. Anand Krishna.
There are 75 participants.
Okay.
So we have, you can see,
Hello.
dear colleagues, we have people from all corners of India, north, south, east, west, everybody is here.
Mhm.
And I am from your far west.
কিন্তু আজকে আমি সারাদিন খুব ব্যস্ত আছি, অনেকগুলো ওয়েবিনার আছে। স্ত্রী তো মারা গেছে।
Sir, I am from the far east.
Yes, you are far east.
I am from the far east.
Yes.
कर दो, ये आवाज करता है।
Oh yes.
Okay.
आवाज जाती है।
Professor Velankar sir, namaskar.
Namaskar sir.
Very nice. Professor Velankar from Indore. Yes.
जी नमस्ते।
Central India.
Ravi Bhattacharya ji, namaskar.
Ravi sir, namaskar.
संजय सर नमस्ते।
Very nice.
Namaskar to everyone.
त्यागी साहब.
Good morning, sir. Good morning.
नमस्कार. आपके लिए गुड मॉर्निंग, मेरे लिए गुड इवनिंग.
सर वो कर दीजिए वीडियो स्टार्ट. So now we are going to play that video by YK Vijay sir about our respected beloved Dr.
Oh, yeah.
Khandelwal sir.
Sure.
Technical team, please start.
Good morning. My name is YK Vijay. I am from University of Rajasthan, Jaipur, and President of Regional Council of Rajasthan, RC6. I have the privilege to introduce Professor D.P. Khandelwal, who has been an inspiration to IPT, and I had opportunity to interact with him when he was at University of Rajasthan as a visiting professor. He born on 1st October 1921 and served Mother Earth up to February 1996. He was having a master's from Agra College, Agra, and PhD from Kumai University, Nainital, and he served several places in the country, like Karachi, now in Pakistan. He served as a lecturer at BITS Pilani, Nainital, Agra, Jaipur, and Kanpur at BTI. In fact, his birthplace was Dungarpur in Rajasthan, and then he moved to Agra for higher education, and then Nainital, and the journey started. After retirement, he was an emeritus professor at University of Pune, and he initiated the IPT in 1984 and organized the first national standard examination for physics, and Dr. Gyan Jalsi was invited as a chief guest for the award function of gold medalist, and the annual function of IPT was organized. In the same way, every year he proposed to organize an annual convention, and several programs like NECP, NSEC, NSEP, and NSIP were initiated. Even the NGP for graduate students were initiated during the time, and it continued so far. And NSIP, national level competition for laboratory instrumentation, was also initiated, and I participated in 1990 as the first winner of the gold medal. He initiated all these programs as the leader of IPT, and several people started joining him. He traveled across the country. He organized meetings and lectures regarding the physics education, syllabus modification, and of course the laboratory innovation and laboratory accreditation. He wrote several books. He produced several PhD, 6-7 PhD from HBJ Kanpur, and the IPT member he added. Now we are about 8,500 in the country as well as abroad. He organized several activities and programs here and there in the country, and his good friend Professor Babulal Saraf was here at University of Rajasthan, where he spent as a visiting professor during 1977 to 1978, and he wrote a book, Physics Through Experiment, and that has been liked by many teachers and appreciated all over the country as well as abroad. Government gave a program of CDPE, Center for Physics Education, and he was the key person to encourage that. He appreciated the mechanical systems and the electronic systems and other optical systems designed and developed at CDPE, and even they had a national and international recognition. in particularly the mechanical oscillator, the resonance has been appreciated at American Association of Physics teachers, where Professor Khandelwal contribution cannot be forgotten. We are celebrating this year as a centenary year of 100 years of Professor D.P. Khandelwal's work, and throughout the year we will be having several programs, national as well as international nature. Particularly, we will have the science stage show at different places, and first we are going to start from 28th February this year, and it will continue to go up to February 2022. And throughout the year, we will have several seminars, workshops, and also the Asian Physics Olympiad, which we are planning to come during 2022. I wish all of you enjoy this Science Day celebration with Professor Khandelwal's celebration, centenary year celebration. Thank you.
Shashank.
नमस्कार.
Thank you. So this was about
Namaskar.
Yes.
Our chief guest, Dr. Upinder Dhar, has joined, and our president of IAPT, Dr. Vijay Singh, has also joined. So we are formally going to start this D.P. Khandelwal birth centenary celebration science stage show. Sir?
टाइम लगेगा यूजर नेम पासवर्ड याद है क्या? हाँ
A pleasant good morning to one and all. I, Dr. Uttam Sharma, Secretary IAPT RC09, and your host, welcome you all in the inaugural session of National Science Day celebration. A part of Dr. D.P. Khandelwal birth centenary celebration, jointly organized by Indian Association of Physics Teachers, IAPT, and Shri Vaishno Vidyapit Vishwavidyalaya SVV Indore. It is indeed a privilege to have such distinguished personality over here. Our chief guest, Honorable Vice Chancellor, Shri Vaishno Vidyapit Vishwavidyalaya, Dr. Upinder Dhar, President, Indian Association of Physics Teachers, Professor Vijay A. Singh, General Secretary, Indian Association of Physics Teachers, Professor K. N. Joshipura, former General Secretary, IAPT, and convener of DPK BCC Committee, Dr. S.C. Samantha, all the respected distinguished delegates, speakers, participants who are with us from India and abroad, join us through this virtual platform. Now, I request all the dignitaries to join virtual traditional lamp lighting ceremony and Saraswati Vandana as a tribute to Mother Saraswati, the goddess of knowledge. Technical team, please proceed.
या ब्रह्माच्युत शंकर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती विश्वजाड्या पहा.
चलिए. Thank you very much. Welcoming the guest is a part of code of conduct for the Indian culture. I request Professor Vijay A. Singh and Professor Ken Joshipura to present virtual bouquet to our chief guest, Honorable Vice Chancellor SVV, Dr. Upinder Dhar. Thank you, sir. Now I request Professor P.K. Dubey, EC member IAPT, to present virtual bouquet to President IAPT Professor Vijay A. Singh. Thank you, sir. Now I request Dr. S.C. Samantha, convener DPK BCC committee, to present virtual bouquet to General Secretary IAPT Professor Ken Joshipura. Thank you very much. Now I invite President of IAPT Professor Vijay A. Singh for welcome address and an introduction to Dr. D.P. Khandelwal. Over to you, sir. Please unmute. Singh sir, please unmute yourself.
I'm so sorry. Am I audible now?
Yes, sir.
Okay, thank you. Uttamji, I should begin by thanking SVV for hosting this very important inaugural function in honor of Professor D.P. Khandelwal. So thank you very much to all of you at SVVV. Okay, and let me, with this thanks, let me say that I welcome all participants. They are all virtual, of course, and all of them in this very important centenary inaugural function. And also, I hope that you will all attend this function and gain a lot by it. Experimental physics is the Achilles heel of Indian science education. You know, it is the one thing that is never done properly, and one reason why we have not made great progress. One reason we have not made great progress is because of the fact that we have neglected this very important, crucial field of science education: experimental work, experimental physics. It was very dear to Professor D.P. Khandelwal. It is difficult, I would say, to do justice in a few minutes to this very crowded and very accomplished life of our founding president, Professor D.P. Khandelwal, whose centenary year is this particular year. He was born 1st October 1921. Okay. He led a very full life. He led a very energetic and accomplished life, and he led a life with a lot of leadership, I would say. Let me say a few words about him. He was born in 1921, and when he was barely out of his teens, when he was barely 20 years or 22 years old, he took up freedom fighting. That is in 1941-43. He was in Agra, and he took up the cause of India's independence, and literally he would write notes dipped in his blood and exhort the students to rise against the British. Okay, so he was very committed to India's independence. That is one. He continued his love for the country, of course. He continued his love for science. He had opportunities to join other avenues and more lucrative and powerful positions, such as the Indian Civil Services. He turned it down without a second thought. He joined Agra College. He joined colleges in Jaipur. And finally, he was at Harcourt Butler Institute, Technical Institute, HBTI as it is called, as it was called then, in Kanpur. Okay. And that is how I remember him. I remember him from his HBTI days. Okay. So while doing that, and even much before the Indian Association of Physics Teachers was founded, he did a number of remarkable things. He organized the first teachers syllabi conference in Rajasthan. He got teachers together in Uttar Pradesh, college teachers, school teachers, to shore up the syllabus. He was passionately committed to science education even before he founded or helped found the Indian Association of Physics Teachers. After his retirement, which was, I believe, in 1981, he got down to the serious task of setting up an all India organization of physics teachers. And here is where we are. We are his legacy. Okay. He founded it in 1984. I have to tell you something, that I was there on March 19th, 1984, for one of the first, I think it was March 6th, I'm sorry, 1984, when one of the first meetings was held. I had joined IIT Kanpur on February 15th, 1984 from abroad. And this was one of the first meetings I attended in the city. And I was very moved by the total commitment of some of the teachers who were present there, particularly Dr. D.P. Khandelwal and Professor R.N. Kapoor. And I had a few interactions with him, but unfortunately not too many. But whatever few they were memorable, and they reminded me of a continuing commitment that I myself should make to physics and science education. His commitment to experimental work was second to none. When he did his experimental work on a spectroscopy, he built his own fluorimeter to carry out this work. So basically, now that we buy it off the shelf, everything is bought off the shelf, he did not do that. He just built it from scratch on his own, okay, with the help, of course, of some technicians. But he was instrumental in building his own fluorimeter, and he was continually instrumental in setting up experimental work and in encouraging experimental work. If India, and if our educationists had paid attention to him a little more, okay, than writing innumerable tracts about education and lamenting about science education, they had paid attention to what he had to say and about his work and his emphasis on experimental work, we would have gone far, far ahead. It is not too late. I think this particular inaugural function that we are having is for experimental work and demonstration. We begin again. We renew our vow to continue education, to our commitment, our vow to education, to physics experimental work, right now from this function, from this inaugural function. He was a great teacher, educationist. He was also a leader, I have to tell you. He was a leader of men and women. He led from the front. I remember one incident when he was supposed to appear for a lecture in Christchurch College, Kanpur, and he was running a fever. That was in the late 80s. And this is something that I was told by some other people like Professor R.N. Kapoor. He was being dissuaded not to go. They said, okay, you are not well. You need not go. People will understand that Professor Khandelwal is ill. He cannot make it. But that was not what he was. He was a finer and harder metal. He was made of steel. He went. Even with fever, he went. He sat there for 3 hours. He showed some experiments, and then he came back. So he led, as I said, from the front. He was not a creature of circumstances, but a creator of circumstances. Thank you very much.
Thank you, sir. Now I invite chief guest of today's event, Honorable Vice Chancellor Shri Vaishno Vidyapit Vishwavidyalaya, Dr. Rupinder Dhar, to present welcome address on behalf of our university. VC sir.
Good morning to all of you on this very important and special occasion. Professor Vijay Singh ji, President IAPT, Professor K.N. Joshipura ji, General Secretary IAPT, Professor S.C. Samanta ji, Convener D.P. Khandelwal BCC Committee, Professor So Chorang Hor from Singapore, Professor H.C. Verma, organizers, Dr. Sanjay Sharma, Professor O.P. Sharma, Professor Uttam Sharma, Professor P.C. Dubey. At the outset, I would like to extend a very warm welcome to all of you on this special occasion on behalf of Shri Vaishno Vidyapit Vishwavidyalaya and my own behalf. I am happy to note that we are jointly celebrating D.P. Khandelwal Centenary. In our university, which is a very young university, Shri Vaishno Vidyapit Vishwavidyalaya, we have believed, always believed, right from the beginning, that each and every student must inculcate scientific temper. So, not only offering programs in science, we have also established certain orations to ensure that students inculcate this temper. For example, Aryabhatta Memorial Oration, Vikram Sarabhai Memorial Oration, C.V. Raman Oration, and Srinivasa Ramanujan Oration. Intention is to invite eminent scientists on these occasions for orations so that students can directly interact with the people who have contributed significantly, not only to the society, but to the whole universe through science. Under this series, we had more than 30 Padma Awardees so far. To name a few, R.A. Mashelkar, Anil Kakodkar, Radhakrishnan, and yesterday only, we had Dr. Rohini Godbole from Indian Institute of Science. This is the reason why we were very eager to get associated with IAPT. Yes, last year we were planning to organize the annual conference of IAPT, but due to COVID-19, it could not happen. I'm sure, and in fact eager, to host this annual conference of IAPT in the later part of this year, 2021. I'm also happy to note that Professor D.P. Khandelwal ji used to work in Agra. I am also an alumnus of Agra University and take pride in saying that Agra University has created great scholars in the past, and even currently also there are many great people who have been working in various domains of science. Now on this special occasion, I don't want to take more time. I once again welcome you all on this occasion. Thank you very much.
Thank you very much, sir. Now, I wish to call General Secretary of Indian Association of Physics Teachers, Professor K.N. Joshipura, to share the overview of the National Science Day celebration, a part of D.P. Khandelwal birth centenary celebrations. Joshipura, sir. Sir, please unmute yourself.
Yes. Okay, fine. Can you hear me, please?
Yes.
Oh, thank you so much, Dr. Uttam Sharma, Honorable Vice Chancellor, Dr. Upendra Dhar Sahab, our President of IAPT, Professor Vijay Singh, Dr. Samanta and his team. It's indeed a great pleasure to welcome you all at this juncture, the National Science Day plus the DP Khandelwal Memorial Program. Yes, Professor Upendra Dhar, sir, you rightly pointed out that one of the aims and objectives of National Science Day is to work for promoting what is known as scientific temper in students and teachers. That is also one of the objectives. We are indeed very thankful to you, Honorable VC Sir, that you have provided us the Zoom platform. You have been kind enough to be here as the chief guest, and we have so many other programs. Yes, in future also we are going to collaborate with you. Friends, I wish to tell you briefly that we are meeting today at the juncture of three important coincidences, kind of triple point in time. The three things that I have in mind and I wish to share with you is one, of course, Professor D.P. Khandelwal Memorial, this celebration, Centenary celebration, which will be throughout 2021. The National Science Day is today. And the third thing is that in the year 2021, we have entered 100 years of a glorious golden decade of Indian science. And that was 1921-1930. And we remember at this juncture the quantum Indians, the trio, Raman, Saha, and Bose. They led us to the international arena. And so three things have come together. It's a wonderful coincidence. The golden decade, 100 years of the golden decade, Professor Khandelwal's birth centenary, and of course, National Science Day today. Raman, Saha, Bose, all of them work for science. They work for promoting science. They were excellent teachers and mentors, as you know, and then their students also. That means, for example, Professor Raman's student, Dr. Vikram Sarabhai and Homi Bhabha, they led to the further developments in the country in the field of science and technology. Today is the occasion to remember all these three people. The first generation is, of course, Raman, Saha, Bose, then followed by others. And now we have a situation where rather than individuals, it is the institution that works. It is also a pleasure to remember fondly, with respect, Professor D.P. Khandelwal. I have occasions to meet him on in two different events in Gujarat, both of them. And experiment was at his heart always. He believed and he promoted learning by doing. That is what I have seen in him. And spectroscopy, as Professor Vijay Singh pointed out, was really fascinating for him. So it is very appropriate that we celebrate the birth centenary with this program. Of course, the very first program was held on the 1st of October 2020 at Midnapur, Center of Scientific Culture. And now this is the nationwide program where our experts will be giving lectures. Not just lectures, they will be giving demo lectures, experiments and demo. So the idea is to promote experiment, and I'm sure it will be very well received. The happier thing is that all the videos of the lectures will be preserved. We have IAPT, our channel, YouTube channel, and even in future, our students and teachers all over India can be benefited through these lectures, and the program is going to continue. Today we have lectures, tomorrow also experts will be coming, and it is indeed a feast of things. So with these words, I am very happy to be here with you. I extend my thanks to all those who have worked and all the speakers who are going to deliver their expert lectures. Thank you so much. Dhanyawad.
Chai mara lage?
Geeta madam, please mute yourself. Geeta madam, please mute yourself. Thank you. Now I request convener of this event, Dr. S.C. Samanta to share about D.P. Khandelwal Birth Centenary Celebration Program. Over to you, Samanta sir. Samanta sir? Hey? Where? Please unmute yourself, Samanta sir.
Sorry.
Yeah.
Good morning to everybody. Honorable VC, Professor Bijoy Singh, Professor Joshipura, and others. We are initiating today the activities for celebrating the birth centenary of Professor D.P. Khandelwal. Dr. Khandelwal, who had a break in his studies due to his participation in Bharat Chhado Andolon in 1942, used to think that for the reconstruction of the newly independent country, most importance should be given for imparting better science education in general and physics education in particular. For these reasons, leaving aside the lucrative jobs, he opted for physics teaching. Throughout his entire life, he remained engaged in developing appropriate physics curricula at different levels, designed experiments for elucidating certain scientific concepts using inexpensive materials, and authored articles and books on them, and finally founded our beloved organization, the Indian Association of Physics Teachers, with the objective of betterment of physics education. But what is betterment of physics education? Everyone has said today that it is meant to develop scientific temper. It means that education should be imparted through scientific argumentation and experimentation. With these things in mind, the IPT has proposed a set of activities. We shall try to write his biography, collect his scattered works, and publish articles dedicated to his memory. Now, I really request, in this opportunity, request everybody to contribute regarding writing articles about his memory, writing about his experiments, and anything you like that will be consistent with the object, with the thought and action of Dr. D.P. Khandelwal. With these things in mind, the IPT has proposed a set of activities. We shall try to write his biography, collect his scattered works, and publish articles dedicated to his memory. Right now, status of lab-based education is not in good shape, as Professor Bijoy Singh has already commented, and others also. We shall try to estimate the exact status and suggest remedial measures. We shall try to popularize physics experience, an activity which was very dear to him. Our members have shown that it is feasible even in pandemic. Today, as part of the National Science Day celebration, we are organizing science stage show. During IPT convention, he used to invite people who used to develop and present such shows. I can still rather it is in my mind that Devdas, Mr. Devdas actually used to organize demonstration participate demonstration experiments. It was a very good 3 hours. It's just like a drama, and I think today we shall get from our own IPT members some such that shows from them, and it is really helpful, at least for attractive other streams from other disciplines to science and physics particularly. So we are actually starting our activity with this stage science show, and we have renamed this Khandelwal Stage Science Show. So in future also, as Professor Joshipura also told, in fact, each presenter will have only 20 minutes show. They have got enough number of shows, I know, that will actually span over hours together. So we shall be having these things in our YouTube, and everyone can really pay those things from our YouTubes. Thank you.
Thank you, Samanta sir. So gradually now we reach to the end of our inaugural session. I once again thanks to all the dignitaries and delegates present through this online platform. Now it's time to start our session 2. I would like to invite Dr. P.K. Dubey, EC member, IAPT, to invite Dr. Anant Krishnan, coordinator of Khandelwal Stage Science Show. Over to you, Dr. Dubey.
Thank you, Professor Uttam Sharma, for giving me this opportunity to introduce Professor Anand Krishnan. Professor Anand Krishnan served St. Paul College, Kalamesri for a long period of 30 years of his service and retired from there as professor and head physics department and research center. He is having 62 research papers to his credit, has written 2 books, and he also worked as a guest faculty to the college and Kerala University. At presently, he is EC member. He served as convener national competition in innovation in physics experiment under the aegis of IAPT. He has given nearly 500 shows, stage shows to different schools, UG, PG, colleges, university places all over India. Although he is 75 plus, but his young, dynamic, dramatic presentation of various scientific fundamentals in physics. And he's behind, he's coordinating this Khandelwal Science Stage Show program in a very nice way, which we are going to see. I welcome Professor Anand Krishnan. Over to Professor Uttam Sharma.
Yeah, thank you, sir. I welcome Chairman of the session, Professor T.R. Anand Krishnan, and request him to give an introduction to Khandelwal State Science Show as conceived by DPK. Over to you, Anand Krishnan, sir. Please unmute yourself. Sir, Anand Krishnan, sir, please unmute. Please unmute yourself. Yeah.
Okay. Am I audible now?
Yeah.
Yes, sir.
Okay. Good morning, everybody. The IAPT faculty, the family, part of the family is here now, listening to and seeing some of the cornerstones in the history of this great organization, IAPT, founded by late Professor Khandelwal. As Professor Samantha, the general convener of this centenary celebrations, rightly pointed out, we have different committees, and I am the convener of the stage show programs organized by IPT, and the session 2 marks the dawn of these programs, which are to be stored in the IPT website, IPT YouTube. Anybody in India, any teacher, any person other than a teacher, even an engineer. In fact, Devdas was an engineer. Dirac was an electrical engineer who got Nobel Prize in physics later on. Can give any of their interested subjects in the stage show form. As you have noted, the title is Khandelwal Science Stage Show. It is not a physics stage show. So anything under science, mathematics, biology, the structure of corona, whatever, can come in a stage show program. Since we have to remember about our Professor Khandelwal, in my introductory talk, let me recollect my first meeting with Professor Khandelwal in 1994, when I came to Amritsar, being invited by him. Even before that, I came across a beautiful article he had written on the science education scenario in India, which came in the bulletin. At that time, I was much younger, as against Professor Dubey remarked my age off. But then I questioned some of the views of Professor Khandelwal about his assessment of Indian scenario of school college educations. So it was with an objection to what he was thinking that I started my relationship. Always, sometimes when we start a relationship with a quarrel, it inevitably ends with a great friendship, as history proves it. So he was asking me what to do in correspondence. So I said, we should know, first of all, what is the scenario in India, in Assam, in Punjab, in Kerala, in Tamil Nadu, in Andhra Pradesh. The style of education is totally different. Especially the lab scenario is wonderfully bad. Most of the schools do not have any lab at all. +2 education, the lab programs are running behind the time schedule. Are we doing justice? So he totally agreed. And then he suggested we should have a national survey. So we did it, and he invited me to present the survey report. I think in convention at Amritsar, Professor Virk was the convener. Another interesting that happened that day was the Devdas Say So. In the evening, in Amritsar, sunsetting was quicker. At 6 o'clock, we all met in an auditorium. Surprisingly, the audience number had increased abundantly than what we find in the morning sessions of seminar of IAPT. The hall was full, all lights off. I'm trying to give you a picture of what a stage show is through this. Then the candle flames were there lit on the stage. And suddenly a group of young girls dressed in a dancing pose marched into the stage. Behind it came a big portrait of Michael Faraday. There was an arati for Michael Faraday in a Hindi song. And then Professor Devdas appeared on the stage and started his demos on Faraday's experiments. Magnets fell onto the coils, and suddenly the stage was lit by electric lights, full of claps. And then the queen came to the stage like a Shakespearean drama. Professor Devdas put a crown on her head, which was a small round tube light. Then he showed some signal. Suddenly the tube light burned. Maybe RF frequency radiations were lit on it. The audience were spellbound. That was 1.5 hour feast for the audience. Physics was taught totally in a different style. There is a new definition of physics learning and teaching. It was marvelous. And that was probably the first stage show in India. I ran to the stage after that, congratulated Professor Khandelwal, engineer he was though, and I suggested Devdas show should be practiced in IPT. Professor Devdas should teach a group of enthusiastic Indian teachers for the show. All the audience clapped beautifully well, but nothing happened. Years have rolled on. Now the scenario is changed. Now of late in India, there are some stalwarts for stage show. Professor B.N. Das, who is going to show with us, can create a rainbow in the stage. Professor Chakradev has shown more than 2,000 shows in India. Marwaha is a great figure in Indian stage shows arena. So a stage show basically implies science is not taught in the class. Science is learned by seeing and getting excited. We break the standard model of the classroom. We stimulate the students' interest. Interactive discussions follow. As some physicists remarked, humor, play, playfulness, invention, the spirit of exposition, all these things come together in a stage show. And through this, the undercurrent of knowledge flows. Gentlemen, you will be seeing many of the stage shows of the people who have I told. Professor Saul is one of the stage show masters in the world. I am thankful to Professor Vijayan IIT Madras for introducing Professor Saul, one of the veterans in the world. And when I mention about him, all of you must be remembering Professor Walter Levin of the Massachusetts University. You know, when he demonstrated a simple pendulum, he himself lies horizontally catching on the rope of the simple pendulum thread, which is 200-meter long. And the pendulum oscillates from one end of the audience gallery to the other end. It creates emotion, surprise, wonder, and then his explanations of fundamental principles of physics, I would say, is a role model for all stage show masters. Later on, Professor Khandelwal wanted to have a workshop of all demonstrations in laboratory, and he used to correspond with me. He applied for a financial grant from UGC, but he did not leave it to come true. It was done in Jaipur, where Saraf and Professor Y.K. Vijay-like persons are there. But A.W. Joshi took over for the task of conducting the workshop, which was in Khandelwal's imagination. A.W. Joshi recovered his diary in which he had written about the workshop, and he had decided that I should be one of the experts, which later on Professor Joshi told me. This tells us the great farsightedness personalities like Khandelwal had in organizing laboratory demonstrations and stage shows. I am very happy that this stage show has materialized, this program has materialized. As I mentioned, anyone in India can submit their stage shows. It will be kept in a library. It is an ongoing program which we will enjoy for the 2 days to come. Thank you very much.
Thank you very much, sir. So now we will have the videos of the science stage show. In today's schedule, we'll have first video of Professor B.N. Das, then Professor B. Chakradev, then Dr. P.K. Dubey, then Professor R. Bhattacharya. So each video will be of 22 to 25 minutes. And then if the speakers or the resource person is available just after that video, we'll have some question answer session for 5 to 7 minutes. Those who want to raise any type of question, they can put their question in the chat box. They can put in the WhatsApp group also what we have meant. Because of some technical issues, the limit is right now 100, and this event is completely online on the YouTube channel of Shri Vaishnav Vidyapit Vishwavidyalaya. And then also, if someone is having some type of question or queries, then he or she can ask directly from the resource person or the speaker. I will provide their mobile number and their email IDs also. All these videos, lectures will also be available on the IIPT YouTube channel after completing of this 2-day event. So now it's my privilege to introduce our first speaker, Professor Dr. B.N. Das, a former Vice President, National Executive Committee and active member of Indian Association of Physics Teachers. He is a former President, RC15 Regional Council of IIPT. Dr. B.N. Das is a Physical Science Coordinator of Bose Institute, Kolkata, for organizing workshop for any teachers and students. He is an active scientist, conducted hundreds of workshops all over India in science popularization and science education for middle and high school teachers and students. We welcome you, sir. I request our technical team to start with the video of Professor B.N. Das. Thank you. I request everyone to please mute your
all of you
video also.
to
Audio.
my stage show. And I should mention that I am very much honored for getting this opportunity to do the inaugural Khandelwal Science Stage. And it was been named after Khandelwal because I have met Khandelwal and I know how much he was aspiring about the physics teaching. And maybe because of him, today I am going all over India to do stage shows. I shall present today few activities on the simplest concept of light or optics, usually called visible light. I shall prefer to name my performance as seeing is believing. Because when we see something, we really believe it that this has happened. So, the importance of showing activity to the student lies in the fact that students themselves, when see the activity, first they believe that phenomena actually happens. And they do understand the underlying concept without much explanation. And not only they learn, but also they replicate the activities and enjoy.
Is there any problem? Should I do it from my side?
No, sir, it's okay, sir. It's okay. Now it will start.
Today, we are going to have a lecture on optics. Optics means the light, with the help of that, we can see objects. That means it is called visible light. But one thing you must remember, visible light means as if you can see the light. The light, the electromagnetic wave of which there is a portion which is called visible light, actually that light cannot be seen. We cannot see light. This is very important, that visible light, it means that light by which we can see, but that particular light we cannot see. Let us check with some example. I have a laser torch over here. You see that I am going to shine this laser on this screen. You cannot see the path of the light. The laser is on here, the light is falling here, and we can see the spot only, but we cannot see the path of the light. That means light is invisible, but when light falls on some object or something, light get diffuse reflected from there, and therefore we can see the object but not the light. But we are going to show you that how light really travel in a straight line. Now what I do, if you come over here, I have some chalk dust, and you can take the chalk dust in your hand. Now I have made the arrangement complete. Now you start clapping like this. When you clap, the chalk dust goes in the air, and those dust particle when falls on this, each particle is scattering the light which is falling on them. So now we have another point, another word which is called scattering. Previously we have seen that we talked about the rectilinear propagation of light. In this experiment we shall see by ourselves that this light is really traveling in a straight line. Wonderful. But this scattering, what is scattering? Scattering is something that when light falls on small particles, they absorb the light and then they re-emit in all directions. Now when laser falls on a particle, that particle absorbs energy, and this energy is scattered in all directions. And this scattering also depends on some factor, though in your book it is not given. There is a scattering factor alpha, which depends on the thickness of or the particle size, its volume, wavelength of light, and there is a 2 factor over here. This is called scattering factor. So this scattering factor alpha is given by this. So you can see if the particle is larger, then lambda has to be larger. But I know that as a preliminary lecture, if I talk about lambda, particle size, scattering, you won't be able to understand. Let us get down to a lower concept. What is that? In this experiment, you see that mirror always has 2 layers, and the mirroring is actually behind this. So when laser light falls here, light normally gets reflected from the upper surface, and a portion of this goes down to the lower surface, and actual reflection takes place in the lower surface. So from the lower surface, reflected light goes and it transmitted parallelly to the first ray. So this is the second one. This is first ray, this is second ray. Again, from here there is another ray goes down from the upper surface, and again it goes to this level, and it starts going in this direction. But obviously the second one, which is getting reflected from a mirror surface, is maximum intense. So when you look at this beam, the beam which is being reflected, you can see that the second or central one is the strongest one, and this part, this is weak. Now here is a combination. If I switch off it, gradually the lights will go on, and you will find that inside this practically no light is seen, and as if it is a black box, nothing is inside. But if I on this light, then you can see that a large number of images are coming one after another. Whatever I have used in this box is a normal LED which is previously available. They are not that intense. Nowadays, very intense LEDs are available. If I put the strong LEDs inside, then you would have seen a long veil, as if that is an infinite veil. What I have done, at the back there is a mirror, and at the front there is a colored glass which permits partially. So as it permits partially, some part is reflected back and some part is refracted out. Actually, in a jewelry shop, when you go, you will see both the walls have mirrors, and you can see your infinite number of images in either of the wall.
We have discussed about the scattering of light. Now there is a wonderful experiment on the scattering, particularly the Rayleigh scattering, because you know that in the morning and in the evening, the sun, when rises or sets, it becomes reddish, and also the sky is blue. For that, we have arranged an experiment. There is a glass box in which there is a liquid, and from the left there is a torch light which is passing through that liquid, and it falls on a screen on a table, and you can see there is a reflected image below because the table is made of glass. Now we pour some liquid which is actually very dilute hydrochloric acid. Let me see, the solution in the glass box is the very dilute solution of sodium thiosulfate. Now as the time passes, if we look carefully in the liquid of the box, then we will find it is becoming very light blue, and gradually this blue increases. And if we go to see the patch of light on the screen, that also changing little bit of color. Now still more, if more time passes, then we see the blue color gradually becoming whitish. That is because this is no longer a Rayleigh scattering, but this has become Mie scattering. That means when the particle size increases, then the color effect goes. But because of the smaller particle throughout the length, we can see that the patch of light is gradually becoming oranges and towards red. And particularly the lower part where there is the reflected part, it exactly looks like a setting sun. Now, if still more time is given, then we shall see that that light, the patch of the light on the screen is gradually becoming reddish and gradually intensity becomes very low, and as if the sun has set on the western sky. Let us now see the utility of the two eyes. Why we have two eyes? What is the advantage? Here we can see a lady is sitting with one of her eyes closed, and someone is proceeding with a pen, and there is a glass on the table. So he is asking at what position he should drop the pen within the glass. And that lady was saying that please come forward, come forward. And when it is dropped, it is seen that it is placed out of the glass. Then with the second eye, the other eye, the lady was asked to close the other eye, and then the pen was taken from the front. Initially she said that you take towards me, then she corrected, and again the same thing happens, because when she said drop the pen was outside the glass. This very clearly proves that the two eye help us to estimate the distance, or it gives the 3D perception of a view. Now we are going to create a narrow beam of light for reflection experiment. We can see that a narrow beam is coming out of a torch where there is a slit cut, but the light which will come out, it is a cylindrical wavefront. So to eliminate the sidewise light, we place two blocks of wood. So finally we see the very narrow beam has emitted. Now where we see the cross, actually at that point there is a very thin mirror, and in the mirror you can see the image of the torch. Now on the figure on the left hand side, I take a pencil and put marking on the left side of this beam, and also the reflected beam on the left side. Now if we rotate the mirror, keeping the position of incidence same, then the position of the reflected ray will change. So here, though it is not being shown, I have taken 3 positions of the mirrors, and that has been recorded on a piece of white paper. And from there, we have seen that the angle of incidence is equal to angle of reflection, and also the amount of rotation of the mirror is half of that rotation of the reflected beam, and obviously all the rays are on the plane of the paper. In this picture, we see that a scale is placed in front of a mirror on a graph paper. Both from the scale or from the graph paper, if we measure and if we estimate the sizes, we shall see the sizes of the centimeters, they are all equal, and the object distance is equal to image distance, which is indicated by another piece of paper which is placed with the scale. Now I am going to show you 3 pictures of lateral inversion. All of you have seen the pictures in the book, but here you see the first picture is showing that there is no lateral inversion, though there is written physics, and behind that there is a mirror. In the second picture, you can see there is a lateral inversion where the physics is written, which is placed perpendicular to the mirror, and it is laterally inverted. And in the third picture, you both see the uninverted image and also the laterally inverted image. I am not going to explain it thoroughly. I expect that all of you should think about it and find out the reason why this thing is happening. Refraction. But actually, along with the refraction, there will be always some reflection and also some absorption. Now you can see my apparatus contains a ordinary, previously we have the filament clamp. I have removed the filament. This bulb itself is my apparatus. Now if I pass the laser light through it, through air it will go in a straight line, through water it will go straight line, and we can reflect, refract, everything can be seen. I am going to show you after this that how laser light is being reflected and refracted simultaneously, and also the total internal reflection. Now you see, this is light is traveling in a straight line in air, and light is also traveling in water, so in a straight line. So you see, any particular medium, light always travels in straight line. Now if we pass on from the rarer to the denser medium, which we were just discussing, you can see clearly that a part of the light is reflected and part of the light is refracted. Now if I increase the angle of incidence, the intensity of the reflected beam increases and the refracted beam also decreases. This is a very important law of refraction of light, that when the angle is more or less perpendicular, reflected line becomes weak and the refracted line becomes strong. So from this experiment we can see that when light gets reflected from a boundary, a part is refracted and a part is reflected. But as the angle of incidence increases, you see the reflected intensity is more than the refracted intensity. Now if we go from water to air, what will happen? Let us see. And you see that the light goes straight. Now I gradually increase the angle of incidence. See, in water also you can see a part is getting reflected. In the water also a part is getting, as the angle increases, the reflected intensity in water increases. Now there is no reflected intensity, almost. Refracted intensity is strong, but now the reflected intensity is increasing. If I increase the angle more, then you see there is no refraction. This phenomena is called total internal reflection. That means when light travels from a denser medium to a rarer medium, when the angle of refraction just exceeds the 90 degree, angle of refraction exceeds the 90 degree, then it totally reflected in the first medium. So this is total internal reflection. And if we continue to go further, it is always total internal reflection, and again we come to the rarer medium to denser medium. Here you don't get total internal reflection. That means in total internal reflection always occurs when a particular angle is exceeded. That means the angle of refraction becomes 90 degrees. Now again I just tell certain things, that when ray of light refracted, this is medium 1 and this is medium 2, whatever we find out that this is angle of incidence, this is angle of refraction, then this refractive index mu is normally, it is the refractive index of the second medium with respect to the first. The ray of light will now go from the denser medium to the rarer medium. So this relation we can change it in this way, that instead of mu2 1 we can also write it is mu2 by mu1. And if this angle is theta 2 and this angle is theta 1, then mu2 by mu1, that means this reverse relation will be sine theta 1 divided by sine theta 2. This is the most general formula. That means we can write mu2 sine
theta 2 is equal to mu 1 sine theta 1. Now in case of water, if the refractive index of water is mu w and the angle now becomes the critical angle theta c, then you see it will be sine theta c, and for air if you consider the refractive index is 1 and sine 90, because in this case when it is the falling at critical angle it traces the surface, that means angle of refraction is 90. So now we get refractive index of the first medium is 1 upon sine theta c. By this way, if we know the critical angle from such experiment, then we can find out the refractive index. But I tell you, for the class 9 or class 10 students, I don't think this relation is there, but if it is in your syllabus, better you remember this formula. This is the most general formula for refraction between two medium. Okay, thank you.
Natural and beautiful phenomena, and we see in the sky that beautiful rainbow forms, and the primary rainbow has a color red on the top and blue below. To explain this rainbow, in most of the books it is said that when light enters the single water droplet, that is being refracted first on the top, then reflected, and then again refracted in the other side. But here most of the books say that it is a total internal reflection. That is not the case. I am saying because if you calculate the critical angle for water to air for say red, then the angle will be about 49 degree. But when a rainbow is formed, all of us know that the between 41 to 42 we see the rainbow. When a person is standing on the ground, they see it that is why it is so. But before that, let me tell you that from I and R we can find the relation between them from Snell's law. If you put a value of I, then R can be calculated. And from the geometry of the rays, you can calculate that the incident ray and the emergent ray, if that deviation is delta, that is given by 4R minus 2I. That is in the fourth line you can see. Now we see what we can calculate, that we calculate the incident, reflected angle of reflection, and then the deviation. Let us go to the next slide. We have calculated I, R and delta for red and also for blue, and you see if the angle of incidence gradually increases, I have written here from 30 to 62, you see at 59 degree the delta is maximum. That means red light at 42.36 it will come back, because after that if the incidence angle increases, the deflection of the red light does not increase. So that is the maximum limit of red. And for blue, similarly we can see that at 59 degree incidence it becomes 41.07. That means blue color comes below red. So we see that none of this red or blue, they are totally internal reflected, but they are simply reflected, and that reflection is the maximum angle. So in this picture we see that above the red line, which is from the eye, a person who is looking from the ground, the angle of the red curve is 42.4 degree approximately, and above that there is no light, and red is everywhere below that, because for all the colors red is reflected from that, but the intensity varies accordingly. Similarly, violet light, the maximum spread of the violet is 41. So below 41, red, violet and all other colors are superimposed on them, so we get a very bright whitish region. But above the rainbow we say dark region. If you look at the rainbow very carefully, then we will see that character, and we can do experiment. But in any case, because of the shortage of time, I think I can give you the rainbow. Everybody has seen that primary rainbow has red above and the blue below. But I request all of you, look at the rainbow and see the dark region above the rainbow and the bright region, within the rainbow, and the total internal reflection concept is not correct. Thank you very much.
Thank you, Professor Dr. B.N. Das, for presenting a nice demonstration. Now, since there are no questions in the chat box, I would request the panel, if they have any question or query they want to discuss, a very few, 1 or 2 questions within a 1 or 2 minutes, because we are running short of time also. All these videos will also be available on the YouTube channel of IIPT from tomorrow onward. So if there are no questions, now we shall move to our second speaker.
Actually, I would like to make a comment.
Yes, sir.
Professor Sharma.
Yes, sir.
That because of the constraint of time, I could not show the experiment, because with a round bottom flask, I can produce a rainbow on the wall. It has been produced, but because already I have consumed 25 minutes, so the experiment actually, which is more important, that I could not show. I'm sorry for that.
Okay, no, sir. Thank you, sir. That was nice one, sir. Thank you very much, sir. Thank you. So now our second Khandelwal State Science Show will be delivered by Professor B. Chakradev, active live member of IIPT. He has conducted more than 2,500 science stage shows of innovative and fascinating demo experiment at various places all over the India, in various school, colleges and university, etc. He has received Best Teacher Award from University of Mumbai in 2008. He was awarded Haribhau Mote Award for creating the best science teaching aid. He has also worked as observer on behalf of TIFR for the national level physics Olympiad exam at Kolkata, Bangalore, Kanpur and Patna. We welcome you, sir. I will request technical team to please play the video, pre-recorded video of Professor B. Chakradev. Thank you.
This is a very special thin film diffraction grating. This diffraction grating has parallel lines very close to each other. In 1 millimeter there are 1000 lines. We call it 1000 lines per millimeter. Or you can say 25,000 lines per inch. In 1 inch there are 25,000 lines. And such a thin film, if we hold in front of a tube light, you can see that the tube light is shining, and on the sides we are getting beautiful color bands. Actually, mercury element, it will give lines spectrum. We are getting the first order color spectrum, line spectrum on both sides. See the symmetry and see the brightness of the color lines. Okay, we are getting symmetrical pattern, first order diffraction grating pattern, beautiful color lines are seen. Mercury being an element and bright light source using a tube light and slit. Here we are getting first order as well as second order. Observe that in first order the lines are very near each other, while in second they are well spread. In first order the intensity is large, while in second order the intensity is very small. It is obvious that as we have higher order we get less and less intensity. Here third order is not visible at all. Even if we make oblique incidence, third order goes to the very wide angle. This is a simple pendulum having a thread and heavy metal round cylindrical. You can see the time period of oscillation depends upon length. If it is short length, it is very small time period. If it is long length, it is more time. If it is very long length, you can see that large time period comes. As the length increases, time period also increases. This is not ordinary pendulum. It is a magnetic pendulum. It has got a very strong magnet, neodymium magnet. And this magnet has no attraction for copper because copper is diamagnetic. But here you can see a magic-like behavior shown by copper, and this magnetic pendulum, I am going to make the swing in special way. Observe the motion of copper plate. It is surprising that the copper plate is going around with magnet. Actually, scientific reason behind it, this is diamagnetic, and when a magnet moves over this copper plate, it induces eddy currents, and those eddy currents will have magnetic field generation, and that field will try to stop the motion of magnet. So the copper plate will always try to oppose the motion of magnet, and in opposing this motion, the copper plate is set into a spinning motion. Very interesting demo. It is a diamagnetic. Now if we replace this and make a paramagnetic like this flag, and if I adjust the length of the pendulum so that we are getting almost touching but not exactly touching, almost touching, that much length we have to adjust, and here we are getting that length fit properly. And now you can see that this aluminum slab and this magnet has no attraction. It is paramagnetic, but we can say that if I set the pendulum in motion, I am getting very free oscillations. But if I keep the slab here and leave the pendulum, suddenly it stops. Now question is, it is not touching, but it is stopping. The reason is again the eddy currents and opposition to the motion of magnet. Here is one wonderful demo experiment. I am having a cylinder, a coil having large number of turns, 3000 turns, and a pair of wires going to array of LED, 4 LEDs. They are connected back to back, anode cathode parallel. Now I can show you a magic like flash here. I can shake this and I can generate flash. So by shaking this I can generate flash. It is nothing but Faraday's law of electromagnetic induction. When I make this fast movement, I am getting current generated, and that gives a flash in LED, and that is E is equal to minus d phi by dt, rate of change of magnetic flux with respect to time. But for that you require a strong magnet inside this coil. I am having a very strong magnet kept inside this cylinder, and it is floating in air. In the cylinder it is floating in air. Now you may ask how you can keep the magnet floating. Very simple. At the bottom I am having one more magnet. powerful neodymium magnet also, and there is repulsion, and one more magnet on the top, and there is repulsion. So we can say south-south, north-north, like poles are facing. And I can prove that one magnet is here, one magnet is here, and one magnet is in the center of the coil. So I can say that the two magnets are holding the middle magnet in suspension. It is like a spring, up and down. And here, when I make this up and down, I get flash. But if I make a slow motion, now you are not getting flash at all. Now question is, why there is no flash in slow motion? The answer is very simple. Answer is, when I make slow motion, magnet 1, 2, 3 and coil all are going at the same speed up and down. They are going at the same speed up and down because the inner magnet is kept compressed by this and this magnet by repulsion, and there is no relative motion between inner magnet and coil. And if there is no relative motion, there is no current generation. There is no change of flux, rate of change of flux. So no current, no EMF, and no flash. But high speed motion, there is flash. Okay, thank you. Yes, here is a magic bulb. When I touch these 2 points, you see the bulb is on. Actually, how it works, it is very simple. When I touch these 2 points, some current goes through my finger. That current may be some microamperes, a few microamperes, or a few tens of microamperes. But this current is amplified by very large amount using a Darlington pair of 2 NPN silicon junction transistors. So 2 NPN silicon junction transistors, if they have gain of 100 and 200, overall gain is 100 into 200, that is 20,000. Such a high gain can make the current from microampere to several amperes also. I can show you what is inside this bulb. It is my own assembly creation. You have 2 wires, 1 circuit, 1 battery. It is 3 mobile cells, lithium ion, small 3.7 volt battery, and I am having a circuit in small compact form and LED panel affixed on the top, and if I put it back and I touch, I get conductivity. Now I can touch by right and left hand, I get conductivity. I can touch here, I get conductivity. My forehead also is conducting. Now I can touch here, yes, it conducts. But you can observe that at some places it is somewhat less because ohmic resistance is more. Now many students ask me the question that what is the relation between this right and left hand, or what is the relation between the 2 tips when I touch one finger, or when I touch forehead, what is the ohmic resistance? And this question is very difficult to answer because you can't measure ohmic resistance by multimeter in skin by skin touching. There is a problem with contact and connectivity. But I have invented one method, very simple method, to guess how much is the body conductivity, body resistance. I can show you innovation. I am having a holder. Now I have a bulb fit into the holder, and if I touch the 2 by hand, my bulb is showing. It is very simple holder, and I can touch to my forehead and so it glows, and if I touch by one finger, then so it glows, and if I dip into the water and I have both ends in water, that also will glow. It glows, yes. Now question is how to measure the resistance between these 2. I have developed a method using this lux meter. This lux meter measures the light intensity, and this lux meter has a sensor here, that is LDR like sensor, and it has cover, and when I remove this sensor cover, my sensor is ready for measuring the light intensity. Now I made one very simple setup for measurement of intensity at different places and different locations. Now here you can see that I am putting a slot cover, and by putting this cover I am covering this entire side, and I can make the background also minimum using this box covering. So I am covering using this box also. Fine. I will show you once again. This is the plastic bottle cut, and this is the cover, and I am putting this. Now to cover this transparent, I covered this also. Now I will put this on the top. Now my sensor will get light only from this bulb, because I cut all the surrounding from light. And if I touch this, you can see the glowing. I can see the light. Now if I am able to read this, yes, I can read the current here. I can read the lux here. Now how much is the intensity of light? I can take the reading, and this reading will give me measurement of intensity of light in lux. And I have taken several readings by connecting a resistance. You can see the plenty of resistances are there, and I can connect a resistance between this and this point. That is, I get some current, I get some light, I get some reading, and I can change the range also if I want. Yes, I can change the range, and I can take this reading here also, different R. I can take 1K, 10K, 100K, 1 meg, 10 meg, so many ohmic value. I got a big collection, and every resistance different step by step. If I take the readings for lux, I am able to calibrate my lux meter reading with my resistance, and using that calibration graph, which is a falling graph, common sense, when R will increase, the lux will fall, lux will decrease, intensity of light will decrease. So when I put some mega ohm resistance, I get very less light intensity, and if I put some kilo ohm resistance, I get large intensity, and if I make a short circuit, I get the brightest light. So it is common sense. I am getting this full intensity when short circuit is there, and if I make 1 meg, 10 meg, I get very less. And in a way, I am able to plot the graph and calibrate the whole curve, and this graph is somewhat like this. Okay, you can get the graph, you can get the judgment of the graph, and on this graph, I will now touch by two hands. I get some reading. I touch by one finger, I get some reading. I touch by my two tips to my forehead, I get some reading, and those readings I'll check on the graph will correspond to which R value. Very nice way of guessing the conducting path resistance, and this gives a joy to learn. And I'll tell you some interesting finding. When I short circuit, it is 0 ohm. When I put it in water, it is about 10 kilo ohm. When I put on my forehead, it gives me about 80 kilo ohm. When I have the wet hands, water and wet hands, I get about 100 kilo ohm. If I put two hands press, I get 300 kilo ohm. If I put two hands with loose contact, I get 500 kilo ohm. See, press different and loose contact different, because conductivity changes with touch. Very interesting. And finally, if I use single finger, I get about 800 kilo ohm, because single finger has got high resistance there. So this is one innovative way of measuring unknown resistance using a lux meter. It is intensity measurement, and that's all. Thank you. This is a glass prism using glass plates, which we are using in compound microscope for slides. And I have a screen here, very ordinary white bakelite, and I have got a laser pointer here. You can see that it is having a green spot, but if I make this green beam pass through this pink color solution, I get beautiful golden yellow track. And it is surprising what is the change of color, why there is change of color. Because when we teach college students that when a ray of light goes from one medium to other medium, its velocity changes, its wavelength changes, but its frequency does not change. Frequency remains constant and its color also does not change. But here we are observing that there is change of color, and that is because of the fluorescence. It is a property by which the medium is emitting some different color wavelength, color light. Here, when I make this horizontal, I see the beam go down and down. That is because of double bending by refraction. But if I make this beam to come angle, you can see this is horizontal, and again it is going down. And then this incoming ray, outgoing ray, they are symmetrical to the prism. This is horizontal. We say angle of minimum deviation is achieved, and we can calculate the refractive index of the medium using that delta M. Now you can see one more thing, very interesting. The beam is going back into the same medium. It is because of total internal reflection. Now when a beam passes through the medium, the photons can interact with the molecules, and the molecules will have inelastic collision with photons, and this is called as Raman effect. When the photons collide with orbital electrons, we say Compton effect, and when the photons collide with the tiny particles, very small size particles in the medium, we say Rayleigh scattering, and when the photons have inelastic collision with molecules of the medium, we say it is Raman effect. In the Raman effect, we can get Stokes lines and anti-Stokes lines in the spectrum. Stokes lines have lower frequency, while the anti-Stokes lines have higher frequency. Anti-Stokes lines are very less intensity, very dim. We can observe only in very special instruments and dark room, and it is very difficult to make measurements in daylight. But remember that it is property of that medium, say organic compound or some other liquid or solution or some solid state material, but Raman effect is very important. Start. Here is a very special experiment. You can see a ray of light is going from water to air, a green laser appearing yellowish here and again green here. I will explain you this phenomenon called as fluorescence. Now this fluorescence is giving a track, very special track, and if I change this angle, when the ray comes perpendicular, it goes perpendicular, no change of direction. But if I change this angle from 0 to 10 or 20 or 30, we can observe that this angle is 30, and at the same time I am getting this angle almost 44. So 44 degree and 30 degree. Now this is small, this is large because of refraction. When a ray of light goes from water to air, it bends away from normal, it will deviate away from normal, and this angle is large and this angle is small because denser medium, rarer medium. Now if I make this angle 40, I get this almost 60, and here if I go on increasing this angle, this will go on increasing very fast, and within a few degrees here I get this almost 90, and that is called as grazing angle, and the ray will go almost parallel to the interface, and this angle at that time is called as critical angle, for which this R is 90 degree. So I can say this is critical, and that is almost 48.5 or something. Now if I go beyond critical, you can see that the ray is completely coming back to the water, and that is called as total internal reflection. And this total internal reflection obeys the laws of reflection. For example, this angle I is equal to angle R, and incoming ray, outgoing ray, normal, they are in one plane. Very simple physics behind it. So this total internal is very useful phenomenon for optical fibers and many other applications. Anyway, I can take other way around readings. I can go from air to water, but now this will be large and it will be small. I can take various readings here and readings here. I, R, I can find sin I, sin R and take the ratio sin I upon sin R. I will find that ratio remains constant. It is called as Snell's law. I can verify Snell's law measuring angle. The beauty of the apparatus is that I can take very fine readings in degree. Here we can see one more phenomenon, and it is reflection. This is partial reflection because some ray comes, some energy comes here, some energy comes here. It is called a division of amplitude or division of intensity or division of energy, and we can get this reflection more and more bright when this angle becomes large. You can see this, you can see the brightness is more here. At this angle, when it goes to 90, we get very bright. Very interesting phenomenon, dependence on the angle of incidence. Now this apparatus is my own design, idea, fabrication, carpentry, assembly, everything at my home, in my workshop, in my lab, and I give a name also. The name is Tyroscope. TIROSCOP. TIR stands for total internal reflection and O stands for observation. So I can observe TIR. That is why it is Tyroscope. It is my own creation, my contribution to physics. Thank you.
Awesome. Thank you. Thank you, sir. Thanks for your nice presentation through the video demonstration. We are receiving lots of comments in the chat box regarding the lecture of Dr. B.N. Das and again by Dr. Chakradev. So there are lots of comments congratulating for the nice demonstration and the way you have made your videos and presentations. And is there any question related to, if anybody want to ask? No, sir. There are heads off. There are wonderful. There is excellent, and many such type of amazing comments for you people on the chat box. So I must congratulate you people. In fact, the two of my colleagues who are working with me as a technical expert, they are asking, sir, at this particular age and at this particular junction, they are delivering their lectures in such a nice way, and definitely you are serving the society in a much better way. Thank you very much, sir. So now I will move ahead to our next resource person or the speaker, Dr. P.K. Dubey, who is my guru also, and who has introduced me to the Indian Association of Physics Teacher, and with whom we are doing all the activities of RC09 along with respected Velankar sir. Dr. P.K. Dubey, professor and head, retired professor and head, Department of Physics, PMB Gujarati Science College, Indore. He did his PhD in accelerator physics from RRCAT and RGPV University. He is an active life member and an EC member of IAPT. He has conducted many stage shows, demonstration experiments, designing and performing of physics stage shows. He has given more than 100 invited talks and designed syllabus of Madhya Pradesh school education, Devi Alya University and different colleges. So now I will request our technical team to please proceed for the KISS number 3 video presentation by Professor P.K. Dubey.
Good morning to all viewers, participants. I am Pradeep Kumar Dubey, Armal, Head Physics Department, PMB Gujarati Science College, Indore. Presently, I am associated with Indian Association of Physics Teachers, Instrument Society of India, Glass Blowing Society, and my main interest is demonstration of fundamentals of physics to students belongs to remote area, rural area, from 9 to 12th. Particularly in those areas where nobody is going to do this type of activity. So my objective is to enjoy physics with the students, and my way of working is that student should do it. In so many programs, the title is Do It Yourself. So students will see, then they will do it, will perform that thing. It happens in many times that I was unable to set the setup, but student came and they set it. So in this Khandelwal stage science show, this theme is related with center of mass, center of gravity. Center of mass is a very beautiful aspect. Means at which the mass of entire object considered to be concentrated. The point, the center of mass, is the point at which entire mass of the entire object considered to be concentrated. And if at this point is given some support, the entire body will be supported and the body will be balanced. You see, we are having a system, and if we find out the center of mass and if we give the support, then the system will be balanced. So we will use thing. First, for this demonstration, I am using a question mark. And this question mark, it's a wooden piece. You can see it clearly. And it is having a notch at this point. And we want that this question mark should be kept at the tip of this finger. And if we keep it here, it will fall down. We want that it should stay here at this tip of this finger. Okay. It's an interesting setup. Students are enjoying this. They are coming to stage and they will see it carefully. They will draw the sketch of this question mark on their copy, and then so for this purpose we are using a belt. This is belt. If you are having a leather belt, it's all right. If you are not having, then it may create some problem. But if leather belt is there, then it will work in a proper way. So in this notch, I will fix this belt. And I'm putting it this at this. So you can see that this if the point where the whole mass of the system is concentrated is given some support, the whole system will be balanced. You can see that I am putting this question mark at the tip of my finger. I will show you the close-up. See this thing. And the other thing I want to show that the lower terminal of the belts, lower end, they are moving towards my hand. See it. They are not going away. They are moving towards. They are toward. So the center of mass is towards this tip of the finger. See it carefully. So this is an interesting setup. I'm using one boy student as a volunteer, and he will keep this question mark on this finger with the help of belt and move throughout this hall. Second thing I want to show, a girl is moving on the rope. If we are going to market, we'll find that a rope is there and this girl is walking on it. So we are having a CD, circular disc is here. And on this, I want to put this circular disc on the tip of this wire, like this. But if I leave it, it will fall down. But the girl can walk on the rope easily. But the situation is slightly different. That girl is having hands and he is keeping away his hand. So the center of mass of the system is balanced. So no hands are there in this circular test. So what we are doing, we are creating hands. So for this purpose, I am using these clips. 4 clips are there, and it is this second one is attached to this one, third one is this one, fourth one is this one, in a similar way, like this.
अरे नहीं, मैं साइड कर दिया था। देखा है तो देख सकते हो, मीटिंग से क्विट नहीं होगा।
इस बीच में फिर क्या एक मिनट कौन सा वाला का था इसमें इसमें शेड्यूल था नहीं इसमें क्या शेड्यूल तो 3 में क्या 3 कौन सा ये 3 है इसमें था
So in this way I can keep this circular disc on the tip of this wire.
ये
So I'm using 4 clips.
ये अभी खत्म होगा
Clips.
12:25 क्या
One is there,
फिर
another
कल
is
भी है क्या ये
And the
एक कब का है
important thing is here, I have to keep these two strings very close to each other. If I want to keep them away, it is not easy to fix this circular disc on the tip. We have to take much more effort. Because these clips are lightweight clips. Weight is low in comparison to weight of the CD. And anyway, if we blow it, you will see that the balance is slightly disturbed. If we'll blow it with, if we blow in a controlled way, then this will rotate on this. Right. Now, in this, I will change the system slightly and doing this one. The same system, both the string have the same pattern. This lower terminal, lower, lower, lower. Again, it is this one. Now I will put like this. This one. This is the horizontal. Here the disc, the CD, the circular disc is in horizontal plane, and it is similar to the flying bird. And the beak is attached to a point, and these are the feather of that bird. If you blow it, now the problem is that these clips are they are lightweight, so the system getting easily disturbed. So we will use some other clips which are having more beds. And we can enjoy the setup. Actually, this beauty of this center of mass, students, particularly school students, are enjoying very much. And seeing this colorful setup, they are coming towards the setup and trying to set it by their own. So I am changing this clips. If some problem is there in the alignment, then it will create problem. See here, in this setup, the clips are having rather more weight than the previous one. So we can fix them in a slightly more distance. The distance between these two strings are higher, more. If I will rotate this one, by rotating the bass, you can see this system is also rotating. By blowing it, the CD is also rotating about this tip. Now, in a horizontal plane, this can be put like this. More vibrations are there, still the whole system is balanced. If you are having slightly uh, thicker clips which are having higher weights, then for more vibrations the balance is there. System is not getting disturbed easily if the weight of the clips is more. So you can see it. By blowing you can make it is rotating about the tip. Easily rotating without getting disturbed. But with those lighter clip, this much movement is not there. Movement is there. Still, if you do it very precisely, you can have this same phenomenon, same effect there. But with this heavy one, it is easy to have this. So, this one is now I'm having one more third setup. I'm having an aluminum pipe. This aluminum pipe. Definitely center of mass, center of gravity is somewhere here. Okay. So this I am keeping like this. I'm putting one more finger here. So if I want, I can, and I'm slightly shifting this finger here. It is like this. Okay. Now this finger is near to center of mass and this finger is away from the center of mass. So if I want to move this finger, I can easily move this finger. But that finger which is near to center of mass, if I will try to move it, so I will find that this is not possible. This finger can move, but the pipe kept on this also move with this finger. It appears that this pipe is fixed with this finger, right? So means if you want, this finger is away from center of mass, this finger is near center of mass, and if you want that this finger which is near to center of mass should move in such a way that this pipe should not get disturbed. This if it moves, then this pipe will get disturbed. Means if we want that this finger should move only and not the pipe, so this will get down, and this can easily move. Suppose, so I am using this property, this that is, suppose this is a house and people are renovating the house. So during renovation, what they are doing, they are removing some beam, column, walls. So as per this demonstration, first they should find out the center of gravity of that house. And suppose this is house and center of gravity is here. So you can remove anything here. The house is not getting disturbed. This pipe is there. It is properly balanced. But if you want to remove anything near the center of mass, this whole system is moving. Means if you remove something near to center of mass, some beam, column, wall, then the whole house will be collapsed. So these are the three different setup which I want to demonstrate, and during this center of mass, center of gravity explanation, and students, particularly school students, enjoy these very much. My phone number is 9425059796. Again, I am this 9425059796, and email ID is pkd. My name is PK Dubey, so it is pkd at the rate tatanagar.com. tatanagar.com. Thank you very much.
Thank you, Dr. Dubey sir, for a nice and interactive presentation. I have posted in chat box the resource person name with their mobile number and email IDs, because we are running short of time, and after every video lecture we cannot have an interactive session as per the schedule. So that's why I have posted name of resource person with their mobile number and their email ID to the Zoom chat box, as well as to the YouTube link also. So further you can contact to the respective speakers and demonstrator. So moving ahead to the last demonstration of science stage show of the day. First, Professor Ravi Bhattacharya ji. Professor Ravi Bhattacharya ji is a active life member IAPT and coordinator IAPT APHO cell. He is the member of the core team for the Indian National Physics Olympiad. Dr. Bhattacharya is an active scientist, science activist, conducted hundreds of workshops all around the India on science popularization and science education for colleges and schools as well as university teachers. He is actively involved in the framing of the syllabus for the BSc Honours Program in Physics at Delhi University. We would like to welcome you, sir. Thank you very much. I will request technical teams to please proceed with the pre-recorded video of Professor Dr. Ravi Bhattacharya ji. Thank you.
Thank you very much for giving me an opportunity to present a state-of-art experiment at the Asian Physics Olympiad. And I'm choosing the APHO 2016 experiment as to showcase a typical Asian Physics Olympiad experiment. Now, this presentation is not exactly a stage show. The stage shows have their importance in initiating students to science as well as enhancing lectures to demonstrate scientific principles. But at the other end, there is the actual act of performing experiments to validate theoretical principles, an essential component of science, since scientific theories have to be validated by definition. The Asian Physics Olympiad is a competition for students of physics who have not entered college. The competition includes an experimental component that tests for various experimental skills. And the various experimental skills that I'm going to talk about, which is tested by a typical APHO experiment, is first comprehension. You can see that the question paper itself is 11 pages long. And the question paper is very detailed. It is a holistic amalgamation of theory, experimental planning, execution, and analysis. The student is supposed to go through all these 11 pages and try and understand what exactly is required from them. Another aim of any experimental component is to relate the equipment and terminology used in the experiment. We can see here that, again, no, sorry. We can see here again that this part of the question paper tells you exactly what are the equipment that has been supplied and a photograph of each of these components out here. Students are supposed to identify these components and then follow the instructions to set up the experiment. Well, every experimental problem in APHO is usually an analog of a research problem, which can be handled by a school student of class 11 or class 12. The APHO 2016 experiment is an optical analog of a reflected high-energy electron diffraction phenomena of a nanostructured ZnSe surface that has a periodic lattice spacing and a non-uniform 1D modulation on the surface of on a nanoscale. So you can see that these are reflected spectrums or diffraction spectrums of the ZnSe, which are shown in these photographs out here. Now, the aim of the experiment is to understand this phenomena with an optical analog so that we can so that we can actually do things on a micrometer scale and therefore is handable. Now, as I said, we follow the instructions given from pages 2 to 5 to set up this thing out here. One can see that there is a circular scale out here. There is a place where the sample is to be placed, a laser diode out here, which is at an angle, tilted at an angle theta, making sure that the light always falls on the center of the sample. And phi is the angle that the grating elements make, grating scratches, for example, make with the z-axis. This is the z-axis. Now, there are 5 samples given in this experimental test. Each sample is a square of dimensions 1.5 by 1.5. Each of this is placed on a holder whose dimensions are 2 centimeters by 2 centimeters, and there is a mark out there which coincides with the 0 mark on the circular scale. So when we put the sample on the table, this mark, one has to be careful that this mark is coincides with the 0 of the circular scale. Now, another very important part of an experiment is data collection. And data collection is an art. Remember, there is a time limit on the students to complete this experiment, which includes reading the stuff, setting it up, and performing the experiments. So, and performing the experiments, collecting data, and analyzing data. Now, it is expected that the students can carry out a judicial mixture of procedures and innovation so that you can manage the data economically. Another important part of all data analysis is trying to linearize data. Why? Because whenever the data can be linearized, then of course straight line graphs reveal interdependence of variables and display valuable information. Plotting a straight line graph is much simpler than plotting curves. And of course, the last part of any data analysis would be to realize the limitation of the experiment in terms of least count of the instruments, systematic errors, random errors, and effective averaging techniques to minimize statistical errors. As we go on, we shall see that judicial questions are asked or questions are posed judiciously so that all this pedagogic aims of the experimental component of an APHO experiment is met. Now, well, we start with the experiment. Sample 1 is a plane mirror. The laser is adjusted so that the spot falls on the center of the sample. The reflection is seen on a graph paper placed at a fixed distance of 15 centimeters. That is the distance from the center of the sample holder to the graph paper. I'll just show the way that we set up this experiment. Here we go, trying to get the laser at 30 degrees. I'm trying to adjust the laser so that we get a spot right at the center, and then it is reflected onto the graph paper out here. This is going to be this is also going to be the 0th order diffraction, I mean the 0th order of the diffractions that we'll get from other samples out here. The task is to obtain the laser tilt angle theta. Let me be honest, even though we have performed these experiments, I'm picking up data, I'm picking up answers from the model answer sheet so that you get a feeling, students get a feeling of how the various skills involved are marked in this paper. So the height, age of the
Hello.
inflected spot is measured, and the distance from the
Hello,
center
Professor Sharma.
is 15 centimeters. From this, we evaluate theta is equal to 10 inverse this. Let me just zoom in this and show you the. All right, this is about 5.5 centimeters, and so we have the theta to be 20.1 degrees. There's a note here which says that in various experiments, theta can be between 19.7 and 20.3, and these are all allowed values. So, all right, data from sample 2. Sample 2 is a steel plate etched with straight, non-uniform grooves parallel to the two edges. Task is to obtain the diffraction patterns and plot them on a graph for phi equal to 30 degrees, 0 degrees, 30 degrees, 60 degrees, and 90 degrees. And this is an actual experimental result. You can see that there is a continuous graph out here.
Hello, my voice is there?
Circular kind of a pattern. Then for phi equal to 30 degrees out there, phi equal to 60 degrees out there, and phi equal to 90 degrees is a straight line. But notice that all this seem to be a continuous kind of a pattern. Now, the task involved with this is to record the diffraction pattern onto a graph paper for phi equal to 30, 60, and 90 of the rotation, and write down the corresponding angle of rotation. So here it is done phi equal to 0, phi equal to 30, phi equal to 60, and phi equal to 90. Sample 3 is a steel plate edged with straight uniform grooves spaced parallel to the two edges with spacing A. Task is to obtain the diffraction patterns and plot them on a graph for phi equal to 0 degrees, 30 degrees, 60 degrees, 90 degrees, and calculate the spacing A and the mean and standard errors. Now you can see that the pattern of the graphs are exactly like those in sample 2, except that right now we do not see a continuous kind of a graph.
Timing?
We see a bright spots out here.
हाँ तो
Yeah.
फिर खत्म हो गया रहेगा.
Yeah. This is for phi equal to 90 degrees, 60 degrees, 30 degrees, and phi equal to 0. These are plotted on a graph. The tasks, the data from sample 3, the task attached is to mark the centers of the diffraction spots from sample 3 for phi equal to 0 onto the graph paper and write down the corresponding angle of rotation phi next to each. So here it is written down phi equal to 90 degrees, phi equal to 60 degrees, 30 degrees, and 0 degrees. The theory of the diffraction patterns from sample 3. Well, basically these are reflection gratings. So whenever the path difference between 2 points is for reflection from 2 different points of the same groove, or adjacent grooves satisfy m lambda is some multiple of the wavelength lambda of the given light, which is of course given 650 nanometers. One can actually get into this condition out here. This relation between y squared and for detailed derivation, one can refer to here reflected diffraction from surfaces. There are 5 authors there, or 6 authors. The American Journal of Physics, 690 to 700. As a solution from here, if phi is 90 degrees, then of course x is equal to 0, and therefore we get a straight line. Various y satisfies this. Place x there. Algebra and y is exactly
उनके साथ डिस्कशन हुआ था, वो लोग 4 आदमी को बुलाया
tasks
and there is agreement. वो उनका क्या कहना, अगर agreement नहीं,
rearrange the thing so that you can write it down as sum in terms of the gradient constant A, write it down as a quadratic, AA squared plus BA plus C equal to 0. And after doing a little bit of algebra, you are asked to identify A, B, and C. And you can see how the points are distributed out here for the calculation of such things. Now, so you take the measured values of y, order 1. Remember the 0th order, we know where the 0th order is. And from there, we measure m equal to 1, m equal to 2, m equal to 3, and so on and so forth. And from there, remember, the equation that we have is a quadratic, and therefore A has 2 possible values. And let me blow this up. You can see that if you look at A1 calculated, they are roughly a constant. Whereas A2, there's a lot of variation out here. Therefore, A2, it is given that the grading constant is a constant. I mean, they are uniform spacing, so we do not take the A2 value and we sit down and calculate from there. Okay. And then calculate the mean for the gradient constant A in meters to 3 significant figures. And so A1, since we have 6 values there, the mean of the gradient constant A can be evaluated by this, and the standard error is this. So the main gradient constant is this much, and the standard error is 8 times 10 to the power minus 8. And you can see that the total tasks is given 0.8 points, and you can see how they are distributed to get the things. Out here, you can see that if the uncertainty in A is within 10%, 10%, then you get full marks. If it is within 20%, you get 0.1 marks, and otherwise you get 0 points. So you have to be very careful. This calculation itself would tell you how careful you have been in measuring your data and how skillful you have been in obtaining the diffraction patterns. Well, that was the task with this. Sample 4 is similar to sample 2, but the non-uniform scratch grooves are at an angle phi star with reference to the 0 degrees, 180 degrees mark of a circular scale. This is an actual data. When we are at 0 degrees, you can see it is no longer circular because there is a certain tilt and therefore the 0 mark is not exactly the lines are not parallel to the 180 mark. So what you do is along the continuous diffracted graph projected on the graph paper, measure the coordinates in centimeter for 10 points starting from -1 centimeters to 35. Enter your results in the corresponding table. And this is done out here. You can see there's a range of values that you can go out there, okay? And from there, you can sit down and you make this table out here. Now, you can, based on the equation 1 given in task D, which was construct a linear equation in the form, this is called linearizing the data. Okay, and let me just zoom this a bit. And this is the kind of a thing that you are supposed to linearize the data on. So that if you, just a little bit of rearrangement and etc., and you should be able to find that mxyd is equal to this, and f is this, and s is tan phi. So plot this. Now, if you plot m versus x, then of course the slope will give you s phi, and this will give you d. This will give you fd. Okay, the intercept. So again, the data are picked up from the model answer sheet. Now, this is the linear plot, and then you look at phi equal to 23.2 degrees. Well, you have been asked to do this, and therefore you have to do this. But there would be a very simple way of getting the thing. You turn the sample till you get a straight line. So if you get a straight line, remember, when do you get a straight line? When the sample, the gratings are at 90 degrees to the incident beam, right? There. But this is not going to coincide with the 90-degree mark of the circular scale. Obviously not, because there's a tilt. The difference in that would exactly give you what is phi star, and therefore phi star is just 23.2 degrees as you get from there. Sample 5 is a steel plate that has non-uniform scratch grooves as well as grooves with uniform spacing perpendicular to the non-uniform grooves. Task is to obtain the diffraction patterns and plot them on a graph for phi equal to 0, phi equal to 30, phi equal to 60, and phi equal to 90. You can see these graphs, right? You can see these graphs. Phi equal to 0, you can see that these are circular things, but you see a lot of them out there. And you can see that the uniform spacings that you have, they are right now at 90 degrees, and therefore the bright spots out here. Similarly with this, right? When phi is equal to 30 degrees, when the non-uniform scratch grooves are at 30 degrees, then of course the other ones are perpendicular to that, and so they would be at 90 degrees, right? And this is at 60 degrees, and this is when the non-uniform grooves are at 90 degrees to the thing. So these are plotted out here. These are plotted out here. These are the points that you see, okay? Okay, these are continuous graphs out here, and okay. So, well, now you have these two gratings, right? So one is a non-uniform grating, and the other is a uniform grating, and they are at 90 degrees to each other. So the pattern that you are going to see is actually a convolution of the patterns of the two things, right? And with that, the distance that you see, if you remember the graphs that we had, okay, the graphs enter the value of B from the graphs that we had. I'll just go back 2 slides and show you that. This will be a measure of B, right? Okay. So from there, you sit down and you rearrange this equation like this at phi equal to 0 degrees, and from there you calculate B to be 2.21 times 10 to the power minus 5 meters. So you can see it is a very novel research problem which has been turned into a very interesting problem which can be handled by students of class 11 and 12 and make them understand the physics behind the patterns that we saw in these zinc selenium structure. Well, that is about it, and thank you very much for this opportunity to enable me present an example of an experiment from APHO. Hope this motivates students to explore and enhance their experimental skills. Thank you very much again.
Thank you very much, Dr. Ravi Bhattacharya ji, for a nice demonstration in this DP Khandelwal State Science Show program. Now I would like to invite our dynamic Secretary of Indian Association of Physics Teachers, Dr. Sanjay Kumar Sharma, for proposing vote of thanks. Dr. Sanjay Kumar Sharma. संजय जी अनम्यूट करिए संजय जी यस
Thank you. Thank you, Dr. Uttam sir, for giving me this opportunity to pay my regards and thanks to everybody. First of all, I would like to say thanks to our chief guest, Professor Upinder Dar, Honorable Vice Chancellor of Shri Vaishnav Vidyapeeth Vishwavidyalaya Indore, for providing us all the facilities to organize this program and also sparing his valuable time to inaugurate today's event. Thank you, sir. I'm also thankful to the President of IAPT, Professor Vijay A. Singh, General Secretary, Professor K.N. Joshipura, Convener of DP Khandelwal Birth Centenary Celebration Committee, Professor S.C. Samanta, and the person in the multidimensional role, Professor Anand Krishnan sir, for taking the initiative to organize Science Stage Show, which was a dream of Dr. D.P. Khandelwal. I'm also thankful to all of you, sir, for constantly guiding us with your valuable suggestions to make this event a big success. My sincere regards and thanks to our resource person, Professor B.N. Das, Professor B. Chakradev, Professor P.K. Dubey, and Professor Ravi Bhattacharya for the excellent demonstration and explaining the concepts of physics so beautifully. Thank you, sir. I would also like to say thanks to Professor U.S. Kushwaha ji and Professor B.P. Tyagi for including the brochure of this program in IAPT Bulletin and in IAPT website. Now, Professor Uttam Sharma sir, hats off to you and your team for devoting so much of your time and taking all the pains for conducting this program so efficiently and seamlessly. Thank you, sir. Thank you very much. I'm grateful to all the participants who registered themselves as well as to those viewing this program live on IAPT YouTube channel. Now, here I want to make one announcement. Although Professor Anand Krishnan sir and Professor S.C. Samanta sir has already told you that these videos will be available on our IAPT YouTube channel, but not only this, whole of the year, we are going to upload various videos of explaining these concepts of physics, and you are requested to see these videos, and as in every YouTube channel, there is a request. I am also requesting, please see the videos, like the videos, and also subscribe our channel. Thank you. Thank you very much. Now, Uttam sir, please invite everyone for tomorrow's program also.
Sir,
Thank
you,
you.
sir.
Thank
Thank
you.
you. Now let me share the program schedule of day 2, March 1st, 2021. We'll start our stage show sharply from 10 a.m. onward. The chairman of the session will be Professor S.B. Velankar, and the stage shows demonstrator or speaker will start from Professor Shao Chong Hair from Singapore. Then we'll have the second lecture by Professor H.C. Verma sir. Then the third one will be delivered by Professor T.R. Anant Krishnan. Then the next one will be delivered by Professor Y.K. Vijay. And in the last, we'll have a lecture, a demonstration video by Professor Sarmishta Sahu Madam. So with that, we will complete our DP Khandelwal birth centenary celebration event tomorrow. I request all of you to please join us tomorrow again at sharp 10 a.m. Because of some technical issue, there was some constraint in the Zoom, but tomorrow it will be able to upgrade to more limit up to 500. So thank you very much to all the invited speakers, demonstrator, guest, participant, delegates, chief guest, and secretary and vice secretary and president of IAPT, and all the post holders. Thank you very much. Jai Hind. So now we are closing this meeting. We'll again sharp meet. I have already shared the link for tomorrow event on the email, through email, and I will share on the WhatsApp group. I will also share an IAPT group, and I will also send to all the respected members of IAPT. There will be a different link to join the tomorrow's event. Thank you, sir. Good day.
Thank you. Thank you.
Thank you.